right? We talked about security. We talked about gRPC. We talked about public key. We talked about double ratchet. And today I'm going to talk about a system where we use this. We kind of put it all together. Does anybody have any questions before we start? All good? Okay, cool. All right, so this is the context. This is the system. Them as the disconnected area, but you can kind of think of this disconnected area can be any kind of area. Maybe it's disconnected because of a natural disaster, like the hurricanes that happened in Florida recently, or maybe it's a man-made disaster, or maybe it's just an impoverished area that doesn't have internet. So, oh wait, I have a pointer. Yeah. So this area is disconnected, and you have people here and they don't have internet. So you can imagine if this person composes an email on their cell phone, that email won't go anywhere because it's disconnected. It'll just sit there on the cell phone. And then you have a connected area, like a city, right? So it's connected. They have internet all the time, just like most of the places here in Ukraine. So they can talk to the internet. And then we have a server in the internet. This server, of course, is always connected to the internet. The difference with the server and these other components of our distributed system is the server is in a location in the internet such that we have total control over it. So if you have a virtual private server or a full server in the internet, you have root password to it. You can easily administer it from anywhere in the world. So we have full control over this server. These other components, we don't have control over. These are private phones that belong to people. And the idea is we want to take this email that this villager composes, and we want to get it sent over the internet. And we want responses to come back as well, okay? So how do we do that? Now, the most obvious way to do it is to get Starlink and set it up in the village, right? And then they use Wi-Fi and you're all done, right? And that can work, that totally works. The thing about Starlink is there's some cost, there's some technical expertise you need on the ground. So there's some impediments to setting up Starlink. So what if we didn't do Starlink? What if we did a zero cost solution? So the idea is there is something that goes between these two areas. We usually refer to this as the bus. Could be a delivery person, could be the postman, right? Could be an aid worker. But there's some transport that's going between these two areas. And in that transport, there's a cell phone. Maybe it's the driver's cell phone, maybe it's a passenger cell phone. But there's a phone that moves between the connected and disconnected areas. Now the key is when this phone is in the disconnected area, that phone is also disconnected because it's a disconnected area. So the bus driver, when it's in this disconnected area, it doesn't have service either. But when the bus driver goes back to the city, the bus driver has service again and can access the internet. Does that make sense to everyone? Okay, so this is where some of the limitations that we talked about with SSL and double ratchet come into play, right? Because with SSL, if you don't have an internet connection, if you don't have a fully connected internet, then you cannot do SSL or TLS between this phone and this server because they're not online, they're not connected. But we can do double ratchet, right? The protocol that WhatsApp uses. So let's look at how we make this work. So just to start off, and am I pushing the wrong button? Let's see. Oh, there we go. Okay. Oops. Wait. Okay. So the actors. Okay, these are the parts of the system. The first part is the server. That's what we talked about. The servers in the internet is trusted and it's managed by a trusted organization. So this server is something that we totally control, we trust, we make sure it's secure. And then the transports, the people moving between the connected and disconnected areas are completely untrusted. We don't trust them at all, okay? They're not managed. We don't control them. We don't know anything about them except that they're moving between these two areas. So they're not trusted, they're not managed. We can identify them. So the server can, when the transport talks to the transport can identify which transport it's talking to. And when the villager talks to a transport, it can also identify that transport. Okay, and then we have the villager. Now I call it the villager, but this is just somebody in a disconnected area. They're also not trusted in the sense that just like my phone is not trusted by anybody but me, right? If my phone were to communicate with your phone, there's no trust that exists between us. So villagers' phones aren't trusted either. They manage their own data. And for this example, we assume they stay in this disconnected area. And the goal is to get end-to-end encrypted communication with the server. So this phone wants to talk to this server, and we need end-to-end encryption. So end-to-end means no one in the middle, namely the transports, can see the data that's getting moved across. Also, transports can't identify villagers. So there's a concept called traffic analysis in cybersecurity, where you can watch traffic, you can watch communication that happens between two computers. You don't know what they're saying, but based on the patterns, you can detect who's saying what, when they're communicating, and maybe you can get an idea of the relationship between the parties, even though you don't see the communication. Does that make sense? Okay, so we don't want that. We don't want that to happen. So we don't want the transports to be able to identify the villagers. So these are the actors. The preconditions, the thing we have set up ahead of time. The server has a public key, and this public key is built into the apps that are used by the transport and the villagers. Okay, so when you use Windows or Mac OS X or Firefox or Chrome, there's certificates built into those apps that say what are the trusted certificate authorities when you do TLS, right? Those are built in. In our apps, in our transport app and our villager app, they're going to have the public key of the server built into them. So they already know the public key of the server, and they know that that public key belongs to the server. Does that make sense? Okay, this is how we bootstrap the key distribution problem. We just build it into the application. And then, of course, there's a private key that corresponds to this public key, and only the server controls that. The private key never gets off the server. And then we have the transports. Transports, when they start up, they generate their own public key pair that they'll use to identify themselves. They'll just generate it themselves. They know the server's public key because their app is built with it. And the villagers also do the same thing. When they start up, they generate a public key pair, and they also know the server's public key. Does that make sense so far? Okay. All right, so this is kind of a very simple startup. Now the goal, here's the goal we have. So the goal of the server, it needs to discover how to reach the villagers. It needs to know the route. So when it needs to send a message to the villager, it needs to know which transports it can use. That's one goal. And then it needs to securely, this is supposed to be securely, securely and robustly exchange data with the villagers. So secure in the sense that when it sends data to the villagers, only the villager can read that data. Transports can't see it. And these transports, we don't trust them. So the server might give some data to the transport and it can just throw it away, right? It can just, or maybe maliciously it can throw it away, or maybe it breaks down and it never gets to the destination. Or maybe its cell phone breaks. Okay, so, and then transports, our goal is that they cannot inspect or modify the data. That's our goal. They have the data, they can try and look at it, right? They get data from villagers or get data from the server, they can try to look at it, but we've encrypted it. So they shouldn't be able to either inspect it or modify the data. And we also want to prevent traffic analysis. And we also want to make it so that a bad transport can't compromise other villagers or other transports. So we don't want, we want to assume that there's bad transports out there, and we want to make sure that they can't compromise other villagers or transports. And then the villager, its goal is to exchange data with the server. It doesn't have access to other villagers' data, and malicious villagers also can't compromise other villagers or transports. Okay, does that make sense? That's our goal. That's what we're trying to do. All right, so here's the architecture that we're using. We are going to, when the transport is in a connected area, it will use gRPC over TLS. So it'll use SSL or TLS to talk to the server on the internet. Now, when it does this communication, we're going to use client-side certificates. Now, this is something that we don't do with browsers usually. You can, at least you used to be able to in the past, but nobody does it. Nobody kind of sets up their own certificate in the browser, and then when they communicate with the server, share that certificate. But TLS has support for that, and we use it. So when we do this gRPC to the server, the transport can verify using the server certificate which server it's talking to make sure it's talking to the right server. And the server, when it talks to the transport, can uniquely identify that transport so that it knows which transport it's talking to, okay? Because of these client-side certificates. And then when the transport's in the village, it uses gRPC over TLS again, over Wi-Fi direct. Now I mentioned, we briefly talked about Wi-Fi direct I think last week, right? Did we talk about Wi-Fi direct? You did, okay, yeah. Yeah, so Wi-Fi direct is kind of a nice little technology. It's usually used for internet printing. That's so that you can go up to not internet printing, network printing. So that you can go up to a network printer and just connect to it and print something really fast. Or you can use it for games. There's a couple of games where you can play a game with somebody that's close to you, even though you're not connected to the same Wi-Fi network, okay? So Wi-Fi direct allows you to establish a point-to-point Wi-Fi connection between these two servers, between the transport and the phone, without any extra hardware. That's the benefit of it, right? And it gives you an IP address, so you can then once you have this Wi-Fi direct connection set up, you're just using normal IP. So gRPC and TLS work in this scenario too. Now, when we do this gRPC connection, we only use server-side certificates. So the client, the phone, the villager phone will connect to the transport and will identify the transport based on its server-side certificate. The transport, on the other hand, has no idea who it's talking to, right? It's just talking to some random villager, and these random villagers giving it random data, okay? Now, this random villager could also be asking for random data from the transport. So maybe on the previous slide, when it Whoops. Sorry. Maybe here, when this transport talked to the server said, oh, I know you're going to see this villager, so here's some data for the villager. So it will send that data to the transport. The transport does not know which villager data is going to. It just gets this data. And then when the transport and the villager are close to each other and establish this Wi-Fi direct connection, the villager's phone will ask for the data that was sent by the server. Now, what we'll see at the very end, how this happens. How does it know what data to ask for? But the transport itself does not know who it's carrying data for. Okay, it will just get these requests for data and it will serve it. Okay, does that make sense so far? Okay, yeah. Yeah.
Sends a message that he wants to buy a thing, bus receive the message, but something had happened, maybe bus driver had lost or
Yeah, exactly. Or he drops his phone, or his phone is stolen. Right? Yeah, or his phone runs out of charge. Yeah, so or it gets reset. Yeah, so there's plenty of situations that could be malicious or could just be accidental, in which the server gives the bus driver the transport some data to send, and it never reaches the destination. That can totally happen, and we assume that will happen. So as part of this protocol, when we send data, either both ways, when the villager sends data to the server and when the server sends data to the villager, we use an acknowledgement protocol. So when the server sends data to the villager, it will give it to the transport to send the data. Now, if there's another transport that's going to the same village, it will give that same data to the other transport as well. So until that data gets acknowledged, until it gets a message back from the villager that, hey, I got that data you sent, it will continue to send data to the villager using any transport that is going to that villager. Does that make sense? So if like let's say there's this bus, let's say this bus here, we'll call it bus number 47, right? Bus number 47, the server had seen that bus number 47 had interacted with the villager in the past, right? So it got some data from bus number 47 from that villager. So it needs to send some data to the villager, and it sees bus number 47 is heading out. So it will give data to that bus number 47, right? And bus number 47 will take off, right? And maybe it will get lost, or maybe whatever happens, the data never gets there, okay? Maybe there's another bus 101, that is also going to that villager. When bus number 101 contacts the server and says, hey, I'm leaving now, the server will look and say, oh, 101 is going to that villager, and will send the same data. Yes.
The user receives the data, make it acknowledged.
Yep.
And then it sends a message that you received the data.
Exactly. It's exactly, I mean, it's the same way like with TCP, right? With TCP, like if you send a packet, if it gets dropped, you just resend it. Yes. Right. He doesn't know. Yeah. You're talking about the server. Yeah. So if the server doesn't get an acknowledgement, Because actually what could happen is, I forgot the numbers I was using, but that first bus 67 goes to the villager, and the server sends some data with bus number 67, and that bus goes, and it gets to the villager, it delivers it, right? But it takes some time for the acknowledgement to come back, right? And then meanwhile, bus number 101 says, I'm leaving. The server will send that same data to the villager. So the data is going to arrive twice at the villager. And so that the villager will just ignore the second one. It won't, it'll ignore it, right? But yeah, so it's basic acknowledgements. It's like TCP. It is like TCP with a huge delay, like TCP with a day-long delay, right? Yes. Right. Yeah. So actually, so for that reason, when we send data, we send the entire prefix. So we send every transport that leaves, we package up all the undelivered data for a villager and send it. So, but the advantage is, the cool thing about this is this link and this link right here, well, especially this link, they're high bandwidth links. So we can send a lot of data. It's just the latency is really high because it takes a while for them to travel. Yeah. Yeah. Oh, yeah, that's a good question. It depends a lot on the environment and it depends on the phone. So, but it's basic Wi-Fi. So, however far Wi-Fi propagates. Yeah. Uh-huh. Yeah. Yeah. So it doesn't cover the whole village, right? You do have to be close to the bus. So I think that's one of the issues that we're looking. So if this bus like stops at a bus stop, you can imagine people at the bus stop or people riding the bus, it's super convenient, right? Because you're at the bus stop or you're riding the bus. So being able to exchange data with somebody on the bus is not a problem. Um, Also in the scenario of a vendor, like for example, one of the incentives for this transport is if you're a vendor, you sell stuff. Maybe you sell food in the village. I don't know what vendors do. But you can imagine this vendor goes to a village to sell things. One of the things that one incentive to buy things from that vendor is villagers can go, and while they're buying things from the vendor, they can exchange data over Wi-Fi Direct, right? So yeah, so one of the things we're looking into to augment this, because this does bring up like the rendezvous problem. You have to, the bus and the villager have to somehow meet, right? And if there is a scheduling problem with that, then it's nice to have something called a Dropbox, where when the bus comes into the village, it can deliver this data to like a stationary. Yeah, it doesn't even have to be a server. It could just be a cell phone, right? Like a cell phone in the bus station, right? So that it can deliver it to that stationary phone. And then that can be like a kind of a buffer between the two. If half the, say it one more time. Yeah, well, so with the Dropbox idea, when the bus sees a Dropbox, it just dumps all its data. Like everything it would transport, it would send it to that one phone. So it would be like a stationary version of the bus, a mirror of the bus. Yeah. Okay. Was there another? Yeah. Uh-huh.
If in Cisco packages, we implement content which includes like server, switch, and several other devices. So if we send a message from a device to a server, it is to go from a switch, like bus in our case. And if it can't reach the server, it's going to switch personal computer. And we will be informed that the message has not been delivered, and we haven't responded. So if the bus breaks during the trip, will we receive a message back that they lost some information?
No, you won't. No, because I mean, even on network protocols, network protocols, some cases you do receive something that a packet was dropped or was lost, but oftentimes you don't. So you can't always count on those negative acknowledgements, right? So yeah, and so here there is no negative acknowledgements, just positive ones. Yes.
For example,
yes. Yeah. Right. Yeah, that's a great question. So how does addressing work? Specifically, what is the address? Like, what is the identity of the different players? So we will talk about that in just a second. I think it's the next slide. Let's see. Yes. Well, okay, this is what we're going to talk about. Okay, so when we use, oops, oh no, going the wrong way. Okay, when we use TLS, we have to have X509 certificates, right? And when we have X509 certificates, we need a certificate authority, right? Somebody like DigiCert that you go to and you say, I'm KPI.UA, right? And somebody at KPI.UA proves that they are that organization, and then you get a certificate back. But in our actor slide, we had no certificate authority. We don't have a certificate authority in this. So somehow we have to establish, we not only have to choose an ID, but we have to choose an ID such that we can securely prove that we are that ID, right? So Amazon.com, for example, or Google.com, when you connect to it, they have this certificate that securely proves that this is the public key for Google.com. We need to do a similar proof. And so what we do is we use something called self-certifying identifiers. Okay, it's a really fancy word for a super simple idea. A super simple idea. Okay, so the idea is when you start up, when a client and a transport start up, they generate a random public key. Okay, they pick a secure random number and then generate a random key pair. So we then need to take that public key and we need to bind it to an identity within a certificate. And we need to do that in a way that everyone else is going to know, okay, yes, or everyone else is going to believe, yes, that ID really does correspond to that public key. So what we do is we make the public key the ID. Okay, so it's a very simple idea. It's a very simple idea. In the system, the ID of each component is their public key. Okay, so they all generate their own ID, thus self-certifying identities. So basically what we do is we base 64 encode the public key, and that's the ID. So for example, here is a certificate, and then the certificate that we get is a self-signed certificate with this public key. So here is an example of the self-signed certificate. You see, here's the subject. This right here is the ID of the client or of the device. And here is here is the bytes of the public key. Okay, we're doing a elliptic curve, so we minimize the number of bytes that we use. So this is the public key, and this is the ID, and this ID is just the base 64 encoding of that. So when we get the certificate, and so when we do TLS and we get the certificate, and we want to make sure that this certificate corresponds to the entity that we think we're talking to the device we think we're talking to, we just look at the certificate and we just have to make sure that the public key in the certificate matches the public key, matches the base 64 encoded public key in the ID. Does that make sense? Yeah. So very simple idea. It's not really that new. It's used quite often in different systems as well. But it does make things very easy, because now we have these certificates that we can trust and can be generated in a distributed manner. We don't have to have any certificate authority to generate them. So also, one thing to note here, we're using TLS only for identification. We're not using it for confidentiality. If you look back here, so the terminating point of these two secure channels, the terminating point is the transport. We don't trust the transport, right? So when we send data over this TLS, the data has to already be encrypted before we send it, because it's going to hit this transport on the other side of that TLS connection, and we don't trust the transport to see the data. So we have to pre-encrypt it. So the only reason we use TLS here is for the different parties to know who they're talking to, so that this villager knows that it's talking to a specific transport, and for this, for the transport to know it's talking to the server, and the server to know which transport it's talking to. So it's just for identity. It's not for confidentiality. Does that make sense? Okay. So we need to get confidentiality, which we'll talk about in just a second. But before we talk about that, I just want to take a quick detour, because this is really hard. You know, gRPC, RPC in general, have people used remote procedure calls? Who's used remote procedure calls? gRPC, or maybe REST. I mean, REST actually, who's used REST? Have people used REST? Okay, a couple of people. Okay, REST isn't as fancy as remote procedure calls. Like, they don't have the nice wrappers around them. But in the end, they're easier to use, because the fanciness of gRPC gets in the way. We'll take a look at that right now. Okay, so let's look at a simple gRPC, and we'll call it TLS test. Okay, this is really simple. We have a service. It has one method in it called test, and it sends a message and it gets a message back. Super simple service, right? And so let's see what it looks like when you implement it. So when you implement it, it's also really simple. So we have a class. This is the TLS test impl. It extends this base class. So this base class is generated from the gRPC compiler to Java. Okay, so I don't know, this looks kind of ugly, not too bad. Okay, but then this is the method we implement, which is super ugly. Okay, it doesn't look that great. I mean, you kind of would expect the method to be test, and then it would take a request, and it would, instead of returning a void, it would return a response. But that's not how they do it. That's not how they do it. Okay, so it's a little bit ugly, still not too bad. So here, we're ignoring the request on this one. We're just saying hello. We're sending a reply that says hello. So we build the answer, we send it back using on next, and then we have to call this on complete to signal that the response should be sent back. Okay, so this is the RPC call. It's not too bad. It's a little ugly, but not too bad. There is a problem though. We're getting a request and we're servicing it, but we don't know who it came from, right? And since RPC is designed to work over the network, you need to know who you're talking to. It's kind of a basic thing to know who you're talking to. So does anybody have any idea or any guess? You can guess. How do we figure out who we're talking to? What do you think? Okay, so there are some keys generated, but how do we get them? Like when we're processing this request and test, how should our code right here get the keys or get the public key, for example, of the requester? Okay. Okay. So we're using TLS for gRPC. So since TLS is going over gRPC, we can use client-side certificates, and TLS will make sure that the client sends the certificate, right? But how do we get the certificate? Because here you see, we really need to get the certificate that's being used, right? How do you think we get it? How should we get it? If you were writing this code and you had to write a line of code here that said, who sent the message? Where do you think it would come from? Any guess? Okay, but how would you get the IP address? But yeah, like how would you get the IP address of the requester? Okay, okay. Okay, but even in that scenario, you are counting on the fact that test can get the IP address. How will test get the IP address? No, but how does it know? Like you'll notice in this callback. So this is where you get so these lines right here, this is where you get to write your code. Okay? You need to like figure out who made this request here. Like somebody invoked test. Some remote client invoked test. Who was it? Who was it? Like you can see the message it sent. It's in request, right? But who sent this request? Yeah. So potentially one thing you can do, and this is what some people do. Some people on test request, they'll add another line there, like another parameter that says who's sending it, right? The problem with that parameter is the client can put whatever they want, right? And so they can lie. We don't trust that. They can lie. So what we really want is to get it from the certificate that was used in the TLS connection. So it would be really nice if it was in request. It'd be nice if you could say request dot get client certificate. That would be really cool. That's not there. Or it'd be really nice if here there was like a, server call dot get requester certificate. Some static. That's not there either. So here's what you have to do. I'm not gonna like delve into this too much, but this is a really important thing to be able to do when you use gRPC. So I just want to like give you an idea so that if you ever have to do this in the future, you can see. Okay, so there's this thing called an interceptor. So in gRPC, you can say, before you process any of the callbacks in any of the requests that come from a server, call this object. Call it, just talk to this object, okay? So you can add this interceptor in. This interceptor is this, okay? So this interceptor, it gets this call, and it turns out that when you use Netty with gRPC, Netty hides the SSL section in an attribute. So you can, in this interceptor, you can get the SSL session that is in use for this call. And with the SSL session, you can get the certificate that is being used by the peer. And when you get that certificate, you can tuck the certificate into a context. That's this right here. Okay. Now, and then, and then I should just, and then right here, this return, this intercept call, this allows the call to then continue and get processed. And now your test callback will get invoked. And now when you're in your test callback, you can call this method. You can invoke get on this client certificate key, and that will give you the certificate. And once you have the certificate, then you can decide. I now know who I'm talking to, because the subject of that certificate will be the ID, the public key, base 64 encoded, of the other side of the caller. Okay, it's horrible. It's really horrible. It's really horrible. And the tragic thing is to do on the client side too. Like when you're a client and you invoke a request on the server, you need to know who the server is. You have to do something similar. There is a GitHub project. You can look at how to do both of them. If you ever use gRPC, you should bookmark it, because this is a useful thing to be able to do. And it's kind of complicated. But by doing this, we can then use these certificates, the X509 certificates that go with TLS, and we can always know who we're talking to when we do our gRPC calls. Does that make sense? Okay. All right. So, let me just, okay. All right. Now, it turns out we're not done. We're not done. Because remember, the certificates we're using, they're not signed by a certificate authority. They're self-certifying certificates. So in Java, in order to make this work, we need to override how Java verifies certificates. The normal way Java verifies certificates is it looks at the certificate chain and it finds this root certificate authority and makes sure that that root certificate authority is one of the ones that are built into the operating system. Okay. And if it matches, if it finds that certificate and all the signatures match, then it lets it go through. Okay. But we're not using certificate authorities here. So we have to create our own trust manager. This trust manager in the end is really simple. It's going to call checks, it's going to call one of these checks, like there's check client trusted, check server trusted. There's a whole bunch of different checks. They all boil down to the same thing, this check certificate call, where we're just going to look at the chain. Since we're using self-certifying certificates, there is no chain. It's just one certificate, right? That is signed by itself. And so we make sure that the chain is length 1, and then we just check and make sure that the base, so this does the base 64 encoding. We base 64 encode the public key. We make sure that it matches what's in the name in the certificate. And if they match, we let it go through. If they don't match, then it fails. Okay, so it's a pretty simple check. But this allows us to do TLS with these self-certifying certificates. Okay, does that make sense? A little bit. Okay, all right. So, but again, we need to get end-to-end encryption, and that's where double ratchet comes in. Do you remember from the last lecture, we had double ratchet? There is some simplifying things here. So first, transport is just an unreliable transport. We don't count on it to do much, except hopefully one of the transports will get data to where it's supposed to go. That's the idea, right? The villagers always talk to one server. So there's one server in the internet. That's where we're trying to get the data to. However, the server talks to multiple villagers. More importantly, the server doesn't know ahead of time who the villagers are, right? Because someone will install this app on their phone and they'll start using it and it should just work. So since the villagers have the server's key built into them, they can initiate conversations with the server. But until that conversation's initiated, the server doesn't even know about the villager to talk back to it. Okay? So let's look what happens. So this is how we start up. So you can imagine this is a new villager's phone. It has the server public key built into it. Okay, this is from the developer, right? So it comes with a server public key built in. When it's first run, it will generate its own public key pair, okay, just randomly. So this is randomly generated. And then our ratchet state, if you remember from last class, there were these ratchets that we have. We initialize that ratchet state to the initial condition, okay? Now, since we have the server's public key here, we can send a double ratchet message to the server, okay? So we do that by sending a data packet. We call these data packets bundles, like bundles of data. So we send a bundle of data to the server. That bundle of data will have one piece of information in the clear, and that's an ephemeral key. Does anybody remember what ephemeral key is? Ephemeral. It's a fancy English word. I was really proud of myself when I learned ephemeral because it sounds kind of cool. So ephemeral means temporary. It means it's created, it exists for a small period of time, and then it goes away. That's an ephemeral key. So what will happen if the villager's phone will create this bundle and it will create a key, just randomly generate a Diffie-Hellman key, and it will put the public side of that key into clear text in the bundle, and then it will encrypt the bundle with the ephemeral key combined with the server's public key using Diffie-Hellman. So that way, when this bundle is sent to the network, the only thing that can decrypt it is the server, because the server is the only one that can use this ephemeral key and its private key to decrypt. Let me just show you. Actually, I have a formula. Yeah. So we're gonna, this key that's generated here is going to be derived from the server's public key and the client's, the ephemeral client key. Okay, so that will encrypt this payload. So this payload will only be visible to the server. It will only be decryptable by the server. So when the server gets this payload, it can then see the villager's ID. The villager's ID is just the base 64 encoded public key of the villager. It can see the transport ID that the villager talked to send this bundle up. Okay, that way the server can learn the routes back to this phone here in the village. It will have the initial ratchet counters, and then it will actually have the data that it's trying to send. Okay, so that will go up to the server. When it hits the server will have this table of that's indexed by the villager's public key, and it will have the ratchet state. And this ratchet state will change as the double ratchet protocol happens. And it will also have the list of transports that it's seen transport villagers' data. Okay, so for example, a transport brought this bundle to the server. The server remembers that transport ID so that later, if it has data to send to the villager and that transport ID is available, it will send data back to the villager through that transport. Okay, so this is for routing. This information here is for routing, and this information here is for encrypting data that it's going to send back down. Okay, so using this ratchet state here and this ratchet state here at the villager, we can do the double ratchet protocol for encryption and send data back and forth. All right, and then so the data can come back down the other way. Let's see. Yeah. So I think we're running out of time here. So the final clarifications. Yeah. So there's when a villager uploads a bundle, how does the server know who it came from and where it's going to? And the second clarification, if transports don't know who a bundle is for, because remember, we don't want the transports to know where the bundle is going to. How do the villagers, when a transport comes into the village, how do they know which pieces of data to request from the transport, right? So the first one, when the villager uploads a bundle, how does the server know where it came from, and how does the transport know where it's going to? Well, when a villager uploads a bundle to a transport, it's only going to the server. It's a one-way trip to one thing. So that makes the routing going up very easy because everything is going to the server. The transporter doesn't care who it comes from. Everything's sent to the server. And then in the encrypted payload of the bundle, we have the client ID. So that's how we know where it came from. Okay. Now, when we're sending back down, it's a more complicated story because when we're sending up, it's only going one place. But when the server sends something, it can go to multiple places. So what we do is when each of the bundles that a server sent is what's called a bundle ID. The bundle ID is simply the client ID and a bundle counter appended to it. And again, the client ID is the base 64 encoded public key. And then this counter is the bundle number that it's sending. So every time it sends a new packet of data to a villager, it will increment that number. Okay, so this is the bundle ID. And then what we do is we have this shared key derived from the server key and the client public key, and we encrypt this bundle ID. So we get this encrypted bundle ID. So by encrypting it, this randomizes the ID, the identifier. So it might be, client 657 and counter 1, and then client 657 and counter 2. But because we're encrypting it, it's going to look random, right? We're going to have random IDs that pop out each time we encrypt the counter. So the only elements of the system that can predict what the encrypted bundle ID is going to be is the server and the villager phone that's going to receive the data. They're the only one that can predict it because they're the only one that can do this encryption operation. So this encrypted bundle ID looks random to the transport and everyone else that happens to see it. But the client, it uses a window. It pre-calculates a window of these encrypted IDs. And when a transport comes into range, it will ask for these random IDs from the transport until it gets one. So if the transport doesn't have anything for the villager will ask for the next 10 bundle IDs that it's expecting, and the transport will say, I don't have that, right? But maybe if the transport has the next ID, then it will ask for the first encrypted bundle ID in that window, and the transport will give it to the villager. And then the villager will say, oh, good, I got bundle 1, right? But maybe what happened was after the villager talked to the server had some data to send to the villager, and it gave that data to the first transport out. Okay, that was bundle number 1. it got sent to the villager. And then the server didn't hear anything. It turns out that transport got lost, right? Google Maps was broken. They never got to the destination, right? So in the meanwhile, another transport comes, and the server has more data to send to the villager. So it generates bundle number 2, right? And then that transport, it was a spy. Like, they were bad, right? They just collected the data and they're like trying to break it with quantum computers or something, right? So bundle 2 never made it to the villager. But another transport came by. The server had more data to send, so it generates bundle number 3 and sends it and gives it to this transport. The transport makes it into the village, right? So the villager's phone is going to ask for bundle number 1. It's going to ask for its client ID plus with 1 appended to it, and then encrypted with a shared key. It's going to be some random bundle ID. It will ask for that, and the transport will say, I don't have that. And then it will ask for bundle counter number 2. And the transport will say, I don't have that. But then it'll ask for number 3, and the transport will say, I have it, right? The villager will get it. It will generate a new bundle to send up to the server. And in that new bundle, it will have an acknowledgement for bundle number 3 that will get sent to the server. So then when that transport gets back to the city, it will send up to the server, and the server will know that the client got, or the villager got bundle number 3. Does that make sense? Yeah. Yeah. So in this case, in this sense, we're different from TCP, because TCP, it is by bytes, right? But for us, it's by 1. So each time we generate a new bundle, we do it by 1. And since we have this window, we do have this situation where we might get stuck. So we might have generated 10 bundles to send to the villager, and all 10 of the transports got lost or something happened. When that happens, we can't generate a new bundle. We just have to keep trying to send that last 10th one until it gets through. Yeah, so it's by 1. All right. Any other questions? Okay. So yeah, so this is the project we're working on. We actually have this implemented for let me go back to the beginning. So the components we use are, this is a Spring Boot server. We Spring Boot here. This is an Android app, and this is also an Android app that we wrote. So yeah, so if you're interested in working on this project, we would love to have you. We have a bunch of students working on it at SJSU. And next week, we can talk about actually the application API, how this looks to the application so that you can actually send data. Next week, we'll be over Zoom because I'm leaving on Saturday. So it's really great seeing you all. Okay? All right. Any other questions? Cool. Oh, yeah. Say that one more time. What explain which? Oh, the first handshake. Right. Yes. Yeah. So the first handshake, and this is the double ratchet handshake, right? That we're talking about. Yeah. So when the let's see, let's go down here. Yeah. Okay. When the villager wants to talk to the server, the villager has to initiate the conversation. The server cannot, because it doesn't know anything about the villager, right? And it doesn't have the villager's public key to start the double ratchet protocol with it. Okay. So, however, the villager can start the double ratchet protocol because it has the server's public key. Okay. So since it has the server's public key, it can start that double ratchet protocol. So this is equivalent to the scenario where we had Alice and Bob that wanted to exchange messages. Bob was offline, and Alice gets Bob's public key and then starts the double ratchet protocol with Bob. Okay, so in this scenario, the server would be Bob, right? The public key of the server is built into the application. So the villager has the server's public key, and thus when they talk to the server, they can start the double ratchet protocol. So these ratchet counters here will be the initial protocol parameters for the double ratchet protocol. Okay, so when the server receives this message, it can then take these ratchet counters and populate its state from this initial message. And once it's populated the state, now it can talk to the villager because it has its side of the ratchet that it can start communicating with the villager. Because if you remember at the very beginning of the double ratchet protocol, the key thing that you need is Diffie-Hellman key pairs. So initially, the client has the Diffie-Hellman key pair because it has the server public key and it has its private key, right? When this message arrives at the server, it has the villager's public key and it has its private key, which is its side of the Diffie-Hellman key pair to start the double ratchet protocol. So once this happens, we now have the state that we need for the double ratchet protocol. And I guess the interesting part about this is on the villager's phone, there's only one ratchet state because they're only talking to the server. That's the only endpoint they're talking to. So they only have one double ratchet state that they need to worry about. The server, though, needs double ratchet state for each villager that it's talking to. Okay, did that answer your question? Okay. Yeah. Oh, yeah. So as part of our build process, when we build the app, we build it in as a resource to the application. So are you familiar with resources in Android? Mm-hmm. Yep. Uh-huh. So when we build the app, the villagers app, and when we build the transports app, when we build both of those apps, we put the server's public key in as a resource to that app. So it's built into the binary of the app itself. Yeah, it's stored in the app. Yeah, in the APK file, the application, along with all the other application code and all the graphics for the app, there's also the public key of the server. Yeah. So that's like the precondition. That's how we avoid the key distribution problem, is we distribute it with the app, which is exactly what happens with operating systems and web browsers when they need to distribute the initial certificate authority keys, is they just build it into the app. Okay. The nice thing about that is when you build it into the app, not only do you build in the public key, but you also build in the trust for that public key. Like, you know, not only the public key, but you know that public key actually belongs to the server. So you don't have that question of, oh, I have this public key. Is it really the server's public key? And the answer is yes, because the app developer put it there. Yeah. No. Because it's built, I guess, yeah, I mean, if we did app updates, we could, I guess if we wanted to update the public key, we would do an app update. Yeah. Yeah, that is a problem. So yeah, if the server public key ever got compromised, it's a problem. It's a problem. That would require an app update, which is kind of a pain to do in a disconnected villager environment. I mean, you can sideload Android apps, but yeah, yeah, that's a problem. Any other questions? Cool. All right. Well, it's great. It's great meeting you. I'm really glad we were able to do this in person. Yeah. Thanks for